Right, good evening folks, welcome. A few new faces, so welcome. My name's Scott, I am the Chair of the West Midlands branch of the Institute of Physics. Mike, and I don't know where Nina is Nina here? Yes. We form what is known as the Keele IOP Physics Centre, of which this talk is one in a series of talks that we put on during the course of the academic year. And so I'm going to introduce our speaker for this evening. This is Assistant Professor Jayadev Vijayan. Jayadev is a Royal Society University Research Fellow and co-director of the Centre for Quantum Science and Engineering up the road at the University of Manchester. He was awarded a PhD from the Max Planck Institute, no less, for quantum optics in Munich in 2020 for work on quantum simulation of ultra-cold neutral atoms in optical lattices, following which he moved to Zurich to work on controlling the motion of levitated mechanical systems. I'm hoping this is right so far. Good. Since joining the University of Manchester in 2023, his group aims to use techniques across atomic physics, optomechanics and photonics to explore foundational quantum science and develop useful quantum technology. So with no further ado, ladies and gentlemen, a nice warm welcome for tonight's guest speaker, Assistant Professor Jayadev Vijayan.
Let me turn this on first. That should be okay. Thank you, Scott, and also Mike for hosting me a couple of hours ago for dinner. Yes, it's a great pleasure for me to be here and have the opportunity to present something about one of my favorite topics, which is how quantum mechanics, something that you would typically associate with the atomic and subatomic scales, might one day be extended to the macroscopic scales that we live in and experience every day. But I'm also extremely well aware that this is a 7 p.m. talk on the 18th of December, which means the holidays are calling and I'm sure you've all earned your well-deserved rest and break. And so I want to make it clear this is not going to be a super heavy and long lecture. Rather, my goal for this evening is to sort of have some fun and share some excitement about the work that we're doing in our lab in order to bring these quantum mechanical systems to larger scales, with larger objects, with more tangible systems, and how we do that in the laboratory. So with that in mind, let's begin with, if you will indulge me in this, I'd like to invite you to take part in a little bit of a thought experiment, okay? Forget that it's 2025 right now. I want you to go back 100 years in time. The year is 1925, and each and every one of you is a first-year undergraduate student at university, and you've just walked into the lecture to learn about modern physics from me as your lecturer. So it would probably go something like this. I would say, welcome, class of 1925, to Frontiers of Modern Physics, where we will teach you all there is to know about cutting-edge physics that's happening today and what that tells us about the universe that we live in. And I want to start this lecture by going back 125 years to 1801, when a chap named Thomas Young in London, he was working on a hypothesis that he had. He was convinced that light is made of waves, but he wanted to find a way to prove it. And now he knew that water is clearly a wave. Like if you have two waves of water hitting each other, they can either constructively add up, this is called constructive interference, or they could cancel each other out, which is called destructive interference. So he wanted to recreate this phenomena using light and see if you can get an interference pattern. If you did, then there would be conclusive proof that light is actually made of waves. So he did the following experiment. He started with a source of light. He sent it through a narrow slit, out of which came these wave fronts that you see here, which were then sent to a double slit, which is just nothing but two slits, one on top of the other. And his hypothesis was the following. If light is made of waves, then each of those slits in the double slit would act as a source of secondary waves. So you'd have one wave emerge from the top slit, another wave emerge from the bottom slit, and they would interfere with each other if you put a screen a bit further down the path. And that's exactly what he saw when he did the experiment. He saw that the two waves that emerged from the double slit would result in this interference fringe of a bit of distance down the experiment. And this interference pattern is nothing but this alternating bright and dark patches that you see on the screen. And that gave him conclusive evidence that light actually does behave like waves. And for 100 years, people thought this to be true, and it is true, until somebody else did an experiment, and this was Philip Leonard. He did an experiment where he was trying to eject electrons from the surface of a metal using light. And he did it the following way. He sent light onto the metal sample, and he tried to increase the intensity of the beam of light until he saw electrons come out. But what he observed was that no matter how intense the beam was that he sent into the metal sheet, no electrons were coming out. And this is a bit puzzling, because if light was a wave, then wave theory predicts that if you send enough intensity of light at any wavelength, there should be some electrons being ejected. But then he found something peculiar. If he changed the frequency of the light, so he made it from a red light source to a blue light source to a green light source, suddenly electrons were emitted. And it didn't matter what the intensity was. Even for the weakest beam of blue or green light, he was able to see electrons come out. Which meant that unlike what classical wave theory predicts, which is that light is a wave and therefore the chance of an electron getting ejected is proportional to the intensity of the light, it's actually proportional to the frequency of the light and not the intensity. And this is a dilemma, because this means that wave theory cannot describe light. And he couldn't solve the problem himself until Einstein came about in 1905, and he said, the only way to resolve this problem is to not think of light in this experiment as waves, but instead to think of them as packets of energy, discrete packets or quanta of energy, who have energy, each of which quanta has an energy that is proportional to the frequency and is equal to h bar nu, where nu is the frequency of the light that is being sent to the metal surface. And so what this meant was, unlike Thomas Young's experiment, which showed that light was a wave, the photoelectric effect seemed to imply that light actually kind of behaves like particles. And that means when you combine the two pictures together, we come to wave-particle duality, which says that light, depending on the experiment that you perform and you want to use it for, behaves like a wave and also like a particle. And it can exist in both of these, or neither of these, if you want to call it that, all the time. And now, I ask you the question, that was all about light, but what about matter? What about the objects that we can touch and feel? Are they like particles or are they like waves? Well, the latest amazing experiments that have been carried out in the past 20 years, from 1900 to 1920, have showed conclusively that if you take any matter, any material, and you zoom in far enough, you would see that everything in this universe is made of atoms. And very recently, we've done experiments to show that if you look inside an atom, you would see a dense, positively charged core, which has protons and neutrons, and negative charges flying around this core. And this system of protons, neutrons, and electrons make up an atom. And every experiment we've done so far has shown that you can think of each of these objects, neutrons, protons, and electrons, as little balls, like particles that are there when you zoom in far enough into any material. And therefore, matter is made of particles and exhibit particle-like behavior. But now you are an undergraduate first-year student sitting in the lecture hall and you're not very convinced by this argument. So you raise your hand and you ask me, but Professor, what if I were to repeat the double-slit experiment with electrons instead of light? What would happen then? I look at you and I say, well, haven't you done your first-year classical mechanics course? This is an obvious answer to this question. If I have electrons coming out of a source, and I do the exact same experiment that Thomas Young did 100 years ago, and I send electrons at this double slit, obviously, anyone who's done classical mechanics knows this, you'd get two lumps on the other side, where one of the lumps is formed by particles, by electrons going through the top slit, and the other one formed by electrons going in the bottom slit. There's nothing else to see over here. This is what's going to happen. I'm a professor, you take my word for it, and you go back to the rest of your course until a couple of years later, somebody actually does that experiment. And what do they find? This is Davidson and German in 1927. They do the double slit experiment with electrons, and surprise, surprise, they find that there's not just two lumps. They see this interference pattern which is reminiscent of wave-like behavior, just like what Thomas Young saw with light. The only way to explain this would be that there's waves of electrons coming from the top slit and the bottom slit, which interfere at the screen, giving rise to this alternating bright and dark fringes. Now you're vindicated or whatever. You're sure that this is the question you asked your professor and he didn't give you the right answer. So you come back to me and you say, look at this paper. They've shown that electrons in a double-slit experiment show wave-like behavior, not particle-like behavior. Right? And I look at this and I say, this doesn't prove anything. Look at that experiment. There's so many electrons, they're charged particles, they're interacting with each other. There's no way for you to say that there was not just some interaction between the electrons happening in the second half over there, which led to these electrons being spaced out like you see on the screen. There's nothing wave-like to this. It can all be explained by interactions between electrons. And you have no counter-argument to that. So, yes, question. Very good. That's exactly the right answer. So you spend decades learning how to do experimental physics. You learn how to operate electron guns. You learn how to build a double-slit experiment. It takes time. So a few decades later, you go back to the lab and you repeat the experiment. You do the double-slit experiment with electrons, but you send them one electron at a time rather than a bunch of them at a time. So it works like this. You send one electron, you wait enough time that the electron goes through the slits and hits the screen. And as soon as you see a spot on the screen, you send the next electron. You wait for it to hit the screen, then you send the next electron. You wait for it to hit the screen, and so on. So by doing this exactly as you predicted, my argument that the electrons were interacting with each other and somehow in this path led to the interference pattern can be ruled out. Nobody knows what's going to happen. We're going to see what's going to happen. But this is exactly the sort of experiment one should design to find out if what I said before was a valid argument or not. And so after this experiment was performed, this is the real data in real time, and each time there's a white spot. That's an electron hitting the detector, and the next electron starts from the gun, from the source. And what you see as a function of time is that it's not two lumps that are formed, but actually there's another beautiful interference pattern in the position distribution of the electrons at the screen. What does that tell you? That tells us that there was no interaction happening between electrons that led to that pattern. Each and every electron behaves like a wave, which means that the only way to explain that pattern in a one particle at a time experiment is that each and every electron must have gone through both slits to create these secondary waves, which then interfere with each other at the screen. That's the only way to explain the results over here. And that's why this beautiful experiment was voted in a poll that was conducted a few years ago by Physics World to be the most beautiful experiment in all of physics until now. And I think that's a fair assessment. It's one of the most beautiful experiments, which showed very clearly that professors can be wrong, but it also showed that matter can also behave like a wave or like a particle depending on the experiment that you perform. Just like light. Light can be particle and wave, so can matter. And this is the wave-particle duality of matter. All right. Let's put things a bit in perspective. So we started with the electron experiment where you shot electrons one at a time. This is in 1927. So that's the yellow balls going around in circles around the nucleus of the atom. And since then, people have tried to create these wave-particle duality experiments. This is called quantum superposition experiments because, as I said, in the double-slit experiment with electrons, the only way for getting that pattern is if each electron had gone through both slits, which means that the electron must have been in both places, the top slit and the bottom slit, at the same time. It's a superposition of being in two different positions at the same time. And so people have repeated this experiment and tried to do this with larger and larger objects. And here on the y-axis on the scale, it's atomic mass units, where one atomic mass unit is the mass of a proton or a neutron. Okay? So an electron is lighter than that, and they did this experiment in 1927. A few years later, they did the same experiment with neutrons and saw the interference pattern. They did it with the whole atom. So this whole object over there, they sent one at a time. Actually, in this experiment, there were many at a time. But they saw the interference pattern, which proved that atoms exhibit wave-like behavior as well. Then they did it with fullerene, which is carbon 60 atoms of carbon in a ball structure, and they saw interference with that as well. And the latest results, 20 years after fullerene, was with a molecule that comprises of 10,000 atoms. Think of that, 10,000 atoms were sent in an experiment very similar to the double-slit experiment, and they were able to observe interference pattern on a screen on the far side, which showed that this molecule, which has 10,000 atoms, was in two places at once, or exhibits quantum superpositions. Their wave nature is apparent in these experiments. And what we do in our lab now in Manchester is to see how far we can push this. Can we keep going heavier and larger until we reach the world that we're familiar with today? But of course, the world we're familiar with today is much, much, much larger than 10,000 atoms, right? Anything that you can think of right now is probably much, much, several orders of magnitude heavier than 10,000 atoms. So we want to go not a small step, but a decent step ahead of, higher than what was previously demonstrated. And we work with nanoparticles. So these are particles made of glass that are about 100 nanometers in size, still very small, 100 nanometers, but several orders of magnitude heavier than the previous record holder for the biggest superposition that's ever been created. And this is a picture from our lab where if you look right in the middle over there, you'll see a glowing green ball. That's the glass nanosphere of 100 nanometers in size that is held in that position by an optical beam. It's a laser beam coming from the side, which is very narrowly focused in the middle and then diverges again. And at this point in the middle where the laser beam is focused, you can trap these glass particles. And because the particles scatter some of the light that is trapping it, you can see the scattered light on a camera, and that's how you know that the particle is there. And the reason we do that is because if you trap it inside a vacuum, you trap it in a laser, then you can put the whole setup inside a vacuum chamber where there's no gas molecules hitting it, there's no noise that can make it move in ways we don't want them to. You want to isolate it as well as possible from the environment because the reason we don't see quantum behavior in our length scales is because we interact with the environment all the time. I might think I'm standing still right now, but I'm actually getting hit by gas molecules all the time, which is making atoms in my body move, and that's way too hot to see any quantum effects for our mass scales. So that's why we take this particle, we put it inside a vacuum chamber where there's almost no gas. You can reduce this to a really, really large extent. And it's not mechanically touching anything else, which could act as a channel through which noise can leak into the system. Okay? Just to give you some context, that's a COVID virus. It's a bit smaller than the nanoparticles that we use. It gives you an idea of how big they are now. Now we come to the big question, which is, I say I have this large object, this nanoparticle. I can say myself, you, the chair, the building, they all exhibit, in principle, they exhibit matter-wave properties. They're dual particle and wave. So how can you make a massive object behave like a wave? This is the question we want to answer. And this is the equation that's relevant for it. The wavelength that's associated with matter, called the de Broglie wavelength, is inversely proportional to the mass times velocity. What this means is that the lighter the object, the larger is the wavelength that's associated with it. The heavier it is, the smaller it is. In my case, I don't think I'm obese, but my wave packet is tiny, tiny, tiny compared to what an atom is, the wavelength that's associated with my matter wave, right? So the game we are playing is not in our favor. When we want to increase mass, we are necessarily decreasing the matter wavelength of the object that we're trying to create quantum properties in. And if you want to see matter-like behavior, you want to increase that wavelength as much as possible. So because we're automatically, by working with larger objects, increasing the mass, the only way to still see wavelength that is decent high is to decrease the velocity. So you're increasing mass, and the only way to compensate for it is by decreasing the velocity, which means that you have to cool the motion of this nanoparticle to a very, very low temperature if you want to see quantum effects start to happen. And this is a pictorial way of thinking about it. Now, when a laser beam is used to trap a nanoparticle, the nanoparticle sits in what is called a harmonic potential or harmonic oscillator, which means that the particle, you can think of it as a bowl that holds, the laser acts as a bowl in which the nanoparticle sits. And depending on how much energy it has, a ball with a lot of energy is going to oscillate back and forth with a large amplitude in this bowl. It's going to go far to the right, far to the left. But if you then cool the motion of this ball, then it's going to move very, very small amplitude in the same bowl. So the bowl is not changing, but the distance the particle moves in the bowl depends on how hot or cold it is. And so if you think of that as the potential, the harmonic potential of the that's given by the laser trap that's holding the nanoparticle, then normally if you just trap it at room temperature, it's going to have thermal motion, or it's going to get moved around by the gas molecules that hit it, and gas molecules have a temperature of room temperature, and so that corresponds to some amplitude of motion of this nanoparticle. And if you want to see quantum effects, you want to decrease the velocity as much as possible, and the maximum reduction in velocity you can get for this particle is by cooling its motion all the way to the lowest rung of your harmonic oscillator potential. So you can think of these as energy levels. And normally when you trap it at high temperature, the particle moves with a lot of energy, and it's at one of the higher levels. But the lowest it can have, it's a limit set by quantum physics, it's called the standard quantum limit, is when you cool the motion of the nanoparticle to the lowest allowed energy level of the trap that it's sitting in. And that is called the quantum ground state. And to put things a bit in perspective, at this quantum limit, if I'm able to cool the nanoparticle to this quantum limit, then my nanoparticle is moving by less than the size of an atom. It's that cold. The spatial extent of its motion, it's an object that's 100 nanometers in size. It's comprised of billions of atoms, but that whole thing is moving by less than the size of an atom. It's very, very cold. And now, before I go further, I think I ought to tell you why we should even do this in the first place. Why do we care about making quantum physics apparent in larger and larger objects? Right? This needs motivation. And there's a few different ways of doing this. I'll do this in two ways. The first one is by asking a simple question. What is the gravitational field of an object, of any object? If I take this water bottle, what is its gravitational field? Yeah? Do you have an answer?
Negligible.
It's very negligible, but compared to the nanoparticle, it's huge. Right? So if you think about it, it's a very good point. That's sort of a picture that you must have seen before. Maybe when you're talking about planets orbiting around the sun, you must have seen that the heavier an object is, the more it bends space-time. And therefore you have these planets orbiting around the sun because it pulls space-time much more, and the planets can then move around it. The planets themselves also pull space-time, but not as much as the sun. So that's how we can know what the gravitational field of an object is, and the orange curve there is the space-time curvature that the object causes when it's sitting in space. Okay? Nothing new here, it's very obvious. The heavier an object is, the deeper the well that it's sitting in, the lighter it is, the shallower. But now I ask you the question, what is the gravitational field of an object that is in a quantum superposition? It's an object that is in a superposition of being here and there. What is its effect on space? Nobody knows this. Because yes, you can create superpositions of atoms. People have shown this, of small molecules. You can do this. But these small objects do not have enough mass to have any gravitational effect. So we need to take larger, more massive objects so that you can start seeing the effect of gravity of these quantum superpositions. And this is a very exciting field of research. One of the big open questions in physics at the moment is what happens when you try to bring these two theories together? General relativity, which is extremely successful at describing the universe and everything else in the classical picture, and quantum physics, which is yet to be proven wrong despite lots of effort over many decades, right? So what happens when you bring these two together? There are some theories which say that the gravitational interactions themselves prevent the formation of quantum superpositions, which means that above a certain mass, the gravitational interactions that it has with its superposition immediately collapses the wave function and prevents these superpositions from even occurring in the first place. That's one option. And these are called gravitational collapse models if you're interested. Or second, something is wrong with general relativity, because that space being both that and that at the same time is not a valid solution that comes out of general relativity. So if it turns out that a superposition of two massive objects can exist and you can measure it, that means that something has to change in general relativity in order to account for spatial superpositions of these particles which distort space-time. And that's, for me, that's a beautiful experiment to perform, because these are some of the most fundamental questions that are open and unknown in physics right now. Is which one of these is wrong when pushed to the limit? Is it quantum physics? It is general relativity? We don't know. And these are the kind of experiments that can try to answer these questions. Second, from a more practical point of view, it turns out that these nanoparticles trapped in optical traps are extremely good for sensing. And what kind of sensing do I mean? I mean, for if you want to build an acceleration sensor. For example, if you want to track where your car or an airplane is going in 3 linear dimensions, but also in different angles, but you don't have GPS, then how do you accurately track the position of your object in all of these 3 linear and 3 angular coordinates? Well, you can use a nanoparticle, because when a nanoparticle is trapped in a harmonic potential, it's moving around in all 3 dimensions, and if it's like an elongated object, and it's also rotating along all 3 rotational axes, right? And because it's trapped in a laser field, you can measure the laser field and send it to a detector, and that detector will tell you how much is my particle moving left and right. So if it's sitting inside a trap, so think of it again as a ball sitting in a bowl. The frequency at which the ball goes back and forth is given by the bowl. And if you're able to measure the particle motion in that, you would see an oscillation that's going up and down in time. So this is in the left side down here, right side up there, left side down here, right side up there, and so on. So you're always tracking the motion of this particle. And now if there's a sudden change in acceleration, if I turn my car left, then I'm going to see that as a signature in the motion of the particle. I'll suddenly see a spike, and then it goes back to its normal oscillation. And by keeping track of how much there's a spike in the x direction, in the y direction, the z direction, I can know very precisely how much the object that the sensor is sitting in has moved left, right, up, down, angles, all of these things. But if you want to do this very precisely, then you want to start with a sensor that's very cold. If it's very hot and the sensor moves slightly, you're not going to notice that change. But if it's really cold, then even the smallest change in acceleration is going to give you a big signal before it comes back to its cold state. And that's what I try to represent there. So you need to cool your motion to this quantum regime, which is the lowest energy level of the harmonic oscillator, if you want to use this as a good sensor. So that's acceleration sensing. You can also use it for gravimetry, which is a field of science that tries to measure Earth's gravitational pull very precisely. You probably know that acceleration due to gravity is an acceleration, so it's just like acceleration sensing, really. And when you take the sensor and move it around the surface of the Earth, depending on what the Earth is made of or above, below the sensor, if there's a big cavity under, if there's a tunnel under there, or if there's a deposit of some minerals, or if you want to measure how fast the polar ice caps are melting, you take it up there and you can very precisely measure what is the mass distribution under it. Because you're measuring the acceleration due to gravity as observable for the mass that's under the sensor. And now if the particle is charged, then you can also use it to measure electric fields. If it's magnetic, then you can use it to measure magnetic fields. It also has applications in gravitational wave detection. You've probably heard of gravitational waves. It was one of the big discoveries of the last few years. And if you remember the videos that demonstrated how these gravitational waves are detected, you would have noticed that the frequency of the gravitational wave was about 100 hertz, 100 times a second. But these sensors over here are oscillating at kilohertz, which is 1,000 times or 10,000 times a second. So if you want to build a detector that is sensitive to gravitational waves at those high frequencies, which LIGO or similar experiments cannot because they work in the low frequency range, then you can use the sensor as well because it's very sensitive in these kilohertz, megahertz range of frequencies. And there are very interesting candidates for what can emit a gravitational wave in these high frequency domains. And this includes dark matter candidates, it includes primordial black holes from the early universe. Lots of these things could result in a high frequency gravitational wave, and if you can detect them, then you give more of an idea of whether these things are feasible and can exist in the universe. I also want to say, well, I was very lucky to get to make a case for these sensors and get funding from the Royal Society, where we're trying to use this technology to build portable, compact sensors that you can take out into the field and measure accelerations and gravity very precisely. But back to the main story. Yeah? So we're back to the double-slit experiment, and now I've told you what we're trying to do is work with these nanoparticles. And that brings us to the question, how do we cool the motion of the nanoparticle? Because if you want to have a good source, then you want to start with your nanoparticle down here, rather than exhibiting thermal motion where it's quite noisy. So the question is, how to cool the motion of a nanoparticle to the quantum ground state? And this is the most technical bit of this talk, so don't worry if you don't understand all of it. It's more important that you figure out what we've achieved at the end. So how this works, how do you cool the motion of a nanoparticle? So the particle is trapped in a laser beam. It's called an optical tweezer because it's like a really sharp focused waist of the laser beam where the particle sits, and by moving the laser you can move the particle around a bit like a tweezer, but optical. So the optical tweezer traps the particle. So if you remember, it has this harmonic oscillation, so it has these energy levels, and the particle is going back and forth, and there's all sorts of energies that are allowed by this harmonic oscillator. Now, the optical tweezer traps the particle, and the particle scatters some of the light that is coming from the tweezer. And then you put two mirrors on the side, such that the light that is scattered by the particle is collected between these two mirrors. They bounce back and forth between the mirror until some of them eventually start leaking out from one of the sides of the cavity, one of the mirrors of the cavity. And then you can send it to a detector. And if you look at the signal on the detector, you would see a spectrum which looks like this, where on the x-axis is frequency, and on the y-axis is the amplitude, the number of photons at that frequency. And you would see many peaks. You'd see 7 peaks over here, and you would see there's one at 0, which corresponds to all the scattering events in which the energy of the photon changed by 0 in frequency, meaning it has the same energy after the interaction with the particle as before the interaction with the particle. And then you'll see 3 on the right-hand side and 3 on the left-hand side. The 3 on the right-hand side have a positive shift in frequency, meaning that the photon has a higher energy after the scattering event. And the only way a tweezer light can have, a scattered photon can have higher energy after the scattering event is if it cooled the motion of the particle. So the motion of the particle was taken away by this photon, and therefore it has to have a higher energy than what came in. You also have 3 on the left-hand side with lower energy than 0, which means that it has contributed to the motion of the particle. The only way that works, so how it works is you have a photon coming in, hits the particle, and comes out with lower energy, which means that the particle now has a higher energy because the photon has given energy to the particle motion. And you see 3 of them on either side because the particle is moving along x, y, and z. So you have each of these peaks corresponds to the particle's motion along each of these directions. And what we do then is we change the length of this cavity to satisfy a very specific condition. And that condition is that the cavity, the frequencies allowed by the cavity, which is given by that blue dashed line, is tuned to enhance all of those scattering events which give the right-hand side, the positive higher energy photons, and suppress the scattering events which give rise to those 3 peaks on the left. And what that means is that once you have this cavity in place, you artificially enhance all of those scattering events which take energy away from the motion of the particle, and you suppress all of those scattering events which add energy to the motion of the particle. So what happens then if there's more events where the particle's energy is being taken away as being given to it, then the particle automatically starts cooling down. Its temperature starts lowering. And it can lower all the way to the quantum ground state where, if you remember, that's the harmonic oscillator. It can be in any of those levels. And if it's, let's say, if it's somewhere, if this is the potential and the particle is sitting there, it can gain a lot of energy. It can still go up. It can also lose a lot of energy, right? But when the particle is in the ground state, it can still gain a lot of energy, but it cannot lose any more energy because it's already at the bottom. So that leads to this asymmetry between a hot particle and a cold particle, asymmetry in the heights of those peaks. And by measuring this asymmetry, we can then use it as a thermometer to extract the temperature of the particle. Does that make sense somewhat? I know it's very complicated, but the whole idea is that you enhance the processes that cool the motion of the particle, and you measure the temperature of the particle by seeing the asymmetry from when a particle is up there, where it can go up and down, whereas when it's down here, where it can only go up, it cannot go down anymore. And you can use that. You do this. We built this experiment in a lab in Zurich, and we did this experiment, and you can see the peaks almost look exactly like you would expect when you do the experiment with the real particle. And we were able to show that you can cool the motion of the particle. On the y-axis there is the number of the rung of your harmonic oscillator. So n equal to 1,000 is somewhere up there. N equal to 0 is the lowest energy possible. And by doing this cooling technique with the cavity, we were able to cool the motion along two different linear axes, x and y, to n less than 1, which is the definition for this lowest energy state of the harmonic oscillator. And I have to say that there are several different approaches being used to cool a nanoparticle, not just the cavity one that I described. Some people also continuously measure the motion of the particle and then apply a feedback force that damps the motion of the particle based on this measurement. So it's like a feedback technique that can also be used to cool the motion of the particle. And both of these techniques have been successful in achieving the quantum ground state. Good. I also want to point out that we spoke about linear motion so far, but there's nothing stopping you from also cooling angular degrees of freedom. So an object that is sort of, vibrating like this, you can also cool that motion to the quantum ground state. And in fact, we can cool it so well, we did this on an updated experiment of the previous one, that we can get much, much closer to n equal to 0 than before. And what this also means is that by some definitions, the particle that we have in there is the most quantum mechanical system ever. It's a mechanical system because it's moving, and it's the most quantum because it's the closest to the quantum ground state. Okay? So where does that leave us? I just told you a big story of how this experiment relates to the double slit. So we go back to the double slit, and if you've noticed, I flipped it 90 degrees. You'll see in a second why I've done that. We were talking about the source. So what have we done? We've managed to cool the motion of the particle, of the particle that's sitting in the trap to the quantum ground state, which means that you have exactly the source that you need to perform the double slit experiment with nanoparticles, because it's now at the lowest energy level. And because it's sitting in this trap that is made of light, what will happen if I turn off the light? If I turn off the laser? What's going to happen to the particle? Yeah? It will, it will go. It can go anywhere, yes. But if you think about it in this configuration, which direction would it go? It will go down, right? With gravity, it would just go down. And that's the advantage of working with optical traps. Unlike, there are some mechanical systems that are like clamped on one side and it oscillates back and forth like this. You cannot turn off the trap in this case because it's physically attached to something. But my nanoparticle is trapped in an optical field. I can just turn off my trap and the particle is going to fall down. And it can fall towards my double slit and later on towards the screen where I can do the measurement. Right? So that's fantastic news because this optical control allows me to do all of these free fall type experiments. But I still haven't addressed the second important point, which is, how do we get the double slit? This is a crucial element of this whole protocol. You need the double slit for the double slit experiment. And it's very challenging. And there's many people around the world trying to do this, and I'll give you a flavor of all of the different things that we're trying to do to recreate a double slit for a nanoparticle. And you can tell me which one is your favorite, and I'll tell you what I'm doing in Manchester. And we can see in 10 years which one works out, right? That's how it's going to be. So going back to the experiment with that, did the double slit experiment with molecules of 10,000 atoms, they used an optical grating instead of a physical double slit. It was no longer a screen with two narrow slits. It was an optical field that was, it looked kind of like that. So you see the periodic green light. So that's the bright and dark parts of a laser. If you send two lasers counter-propagating to each other, then you have the standing wave that's created, and you can use that as a double slit in principle. The problem is, the larger the object is, remember, its matter wavelength is very, very, very tiny. And for the double slit sort of experiment, the matter wavelength needs to be comparable to the separation between two slits. And there's no physical way in which I can manufacture a double slit that has atomic, or actually smaller than atomic dimensions. It's just physically impossible. So that is not the best strategy for larger and larger objects. But there's more promising approaches. The middle one, for example, is really fantastic, is your particle is moving back and forth. It's a continuous variable. Its motion is not either here or there. It's actually moving in all of these places. But can I now force it to be either here or there, which is what the double slit essentially does. The double slit forces the electron wave to go through both of those slits in that position, and all of the other parts of the electron wave is just hitting the screen, but only those two go through. How can I do that with a qubit? I can use a qubit, which is, in this case, they use a superconducting qubit, but you can use whatever is your favorite qubit. It can be an atom, it can be an ion. And the defining feature of a qubit is that it has two well-defined energy levels. It has a ground state and an excited state. And if I can couple this two-level system to the motion of my object, such that if the qubit is in the ground state, my particle's here, and if the qubit's in the excited state, and my particle's here, then I've prepared the double slit. If I can make this happen, then by putting the qubit in a superposition of ground and excited state, I can put my particle in a superposition of left side and right side. And some people do that with clamped resonators, and so the principle works. But the question is, can we do this in nanoparticles? And there's another approach, which is to use nonlinearity, which is if you have a wide trap like that, and you let your particle go from the middle, it can explore parts of the potential which is no longer linear, and that can also give rise to these specific position states of the particle. And these are all valid approaches to solve the problem. And the way we do it in Manchester now, we're building an experiment which uses a variation of the second approach, which is to couple the motion of the nanoparticle to a qubit, where the qubit is not a superconducting qubit, but an atom. So we have an atom over here, we have a nanoparticle over here. They're talking to each other through the cavity. So these are two mirrors in a cavity. So the light that is emitted by this gets trapped in the cavity and eventually interacts with the particle over there. Okay, so the way the protocol works is you have a two-level system, and I can create a superposition of the atom being in a ground and excited state, and by using the interactions through the cavity, I can transfer the superposition to the nanoparticle being in either the left side or the right side. So something like the cartoon is trying to show over there. This is technically very difficult. That's why we have to use millions of pounds in funding to actually build the equipment and the lab and the people needed to build these experiments. But that's what we're doing, and it's a promising approach. Actually, I think all of these are beautiful approaches to this problem, and I don't know which one's going to succeed. I'm more familiar with working with atoms and nanoparticles here, so I use this technique. But someone who comes from a different background might choose something else, depending on what they're good at. And that's how science works. You use the techniques that you know to advance another field of research, or advance your own field of research in a way that nobody else can, because they don't have the same expertise that you do. So that's the approach we take in Manchester. And with that, I can conclude in a way by saying it's a very challenging experiment. It's going to take a lot of effort, but think of the reward. If you're able to pull this off, then we get to reconcile quantum mechanics with general relativity, which is I mean, what other field of research can say something like that, right? This is the benefit of working in a field where you're trying to push quantum physics to heavier and heavier objects, larger and larger length scales, is that you get to answer these important questions that are at the very core of what the fundamentals of physics, in a sense. One of these has to be adjusted. Which one is it? We can answer these questions with experiments like this. And also, in the meantime, while we build the capabilities and overcome the challenges needed to do such experiments, we can use them for other purposes as well, like building the next generation of sensors, which will be able to detect, or which will be able to measure the gravitational field of Earth to the 9th decimal point, which is insane. Like, your g, small g is 9.8 meter per second squared, right? It's not really, it's 9 point something, it's 798, it just keeps going on, it doesn't end. You can go as precise as you want depending on your application. And if you now want to find out if there's a small tunnel under the Earth's surface, let's say you want to build a high-speed train from London to Manchester, and you want to know what exactly is under the Earth, then you want to have a very precise sensor that can measure mass distributions very precisely, which then translates to how well can you measure the value of small g to what decimal point. That's on Earth. You can take this to space. If you want to explore space and find out if there's something under the surface of a moon somewhere or another planet, you take a sensor there and you can just drive it around on the surface of this planet, of this satellite or planet or whatever you want, and you'll be able to map out its underground topology very precisely using this technique, because light cannot pass through the ground. Sound waves cannot go very deep in the ground, but gravity can. Gravity is the interaction that can connect two masses very precisely. So that's a concluding summary, and I just want to say it's a team effort. None of the science that we do is one person's idea and one person's effort. Most of the cooling results that you saw were done at ETH Zurich when I was a postdoc over there, with help from theoretical physicists from Vienna and Barcelona. And right now we have a group that is up and coming. We've had 4 people for about 2 months now. We had one person, Roman, until last year. But now we have 4 people, and we have been very lucky with getting funding to hire more people. So if you're in a stage where you want to pursue a PhD or a project or an internship, you're very welcome to apply. And if not, you wait for a few years, some of you, and you'll be able to get there and apply for solving these very important problems in physics. Thank you.
Thank you, Jayadev. Excellent timing, by the way. Also.